Should I just start from the beginning? I don't think so. Do I look good? Oh, I look fantastic. No way. Quiet, Tim. Fancy. We're gonna do our best to finish this up. Got some reindeer in the back. Hold on. Good afternoon, good evening, good morning, wherever it is where you are. My name is Tim Raschuti, and I am here for your Thursday Math Minute, the only Math Minute guaranteed to be on Thursday. So yesterday, we finished up a video introducing the naive definition of probability and a concept called expected value. And we did this because I recently interacted online with a man named Dan Meyer, and I'm really concerned that his last name is actually pronounced Mayer, but how would I know? I guess I could go back and watch his TED Talk. He probably says his own name, but I usually just read his name. And so if I'm mispronouncing your name, Mr. Dan Meyer, I apologize. So Dan Meyer had this activity. Oh, I should pull the activity up. And in this activity, we're given certain information, and we're supposed to select who we believe was president in some year based on that information. So you can see this is the initial screen where we're just practicing, presuming we know, George W. Bush was president in 05, 06, 07. He was red, of course, so these should be red. He was Republican. So we select who we think was president in a given year. We say check our answers. Yes, nailed it. Got all 16 right. And here's the heart of the activity. We're given some statistic. You'll notice we don't have years now, and we're supposed to select who we think was president. And you can check out the activity yourself. I linked it in the first video's description. I will link it again in this video's description. What I was interested in is that when Mr. Dan Meyer posted some initial results, he said people are only getting these right 48% of the time, worse than random chance. And you remember this whole video yesterday, we talked through how can we quantify the idea that that's worse than random chance? Why is our expectation people should be getting this right 50% of the time? It's certainly the case that we can kind of treat who was president in a given year like a coin flip. And then we eventually worked through yesterday this idea of expected value, where we can average the different results over time for some number of coin flips. And it does turn out to be the case that no matter how many flips there are, you would expect to be able to guess correctly at random 50% of the time. That's the expected value. So we were able to confirm that theoretically. That is, we count up the number of outcomes we're interested in, we divide by the total number of outcomes, and there's our probability. Lots of possible distributions of heads and tails coin flips, and yet when we average out those different distributions over time for some number of flips, you'll always end up expecting to come up heads roughly half the time, 50% of the time. I even got Wolfram Alpha here to figure out for us what happens with 64 flips over time. And again, although it does not list expected value here. Oh, yes, it does. Goodness. Expected number of heads, 32, right there. And it even gives us the distribution of the different outcomes. But then we ran into this issue specifically with the Guess the President activity. Dan Meyer was saying 48%, people answering this correctly 48% of the time, was worse than random chance. And if we treat the selections completely like coin flips, we can see it is worse than random chance. Out of those 64 slides that we can select, we should expect to get about 32 of them right at random. And yet 48%, 0.48 times 64 slides, is just under 31. So people are answering, on average, only 31 of the 64 years correct. And so again, I started to wonder, well, why might that be from a mathematical perspective? That is obviously, in the real world, maybe people just have or don't have certain knowledge, and therefore guess correctly or incorrectly, even as they're trying to get things right. But can we come up with some kind of mathematical justification for why this is happening? And one of the first things I thought of is the fact that presidencies only come in certain runs. You're going to have a president from a given party for 4 or 8 or 12 years at a time, whatever it might be, but you wouldn't randomly guess RD, RD, at least not if you're thinking about the way that the real world works. And so if you wouldn't use those random guesses, is that actually contributing toward reducing our expected value? In which case 48% actually is not worse than random chance. I am not a statistician, I am not a probabilician, which I think is a thing. I'm making it up right now if it's not. But I am someone who loves a good Excel spreadsheet. And so what I wanted to do, if I couldn't initially think through this theoretically, is I wanted to use Excel to help me think through this experimentally. That is, we can just simulate this activity many, many times and see what happens. And then that might give us an idea, oh wow, when we're running these simulations under certain conditions, if people are only selecting R or D for 4 years at a time, since As you may remember from that first slide, people were pretty good about selecting the correct president if they were given the actual year. I made the assumption that people know who was president in what order, how many years a Republican was president, followed by how many years a Democrat was president. But then what I thought to myself is maybe that knowledge is actually causing us to not guess correctly as often when there is some other ambiguity in the system. Either we don't know the answer, or we're not quite sure when a presidency begins because there was some confusion. Barack Obama is elected in 2008. Does that mean 2008 should count as a year of his presidency? No, in Dan Meyer's activity, but you can understand the confusion. But again, I couldn't think through this theoretically. I needed to build out a simulator to help me figure this out. So here's what I built. Let's go ahead and get into it. So the first thing I did is I started to think through, well, what is the distribution of Republicans and Democrats over the 31-year period that Dan Meyer has in his activity? From 1990 all the way through this year, 2020, we have this actual distribution of R's and D's. And so what I built was this little picker. I put a number here, 1, 2, 3, 4, 5, 6, all the way to 16. And this actually started to help me think through why, spoiler alert, it is going to turn out that 50% is our proper expected value. When I built this little thing, it picks a given year to start in. The first year you can start in is 1990. The last year you can start in and have a full 16-year set is 2005. So this is the distribution of presidencies, presuming you start in that given year. And you can see, even though the set itself of 31 years does not have an equal number of R's and D's, 31 obviously is not an even number, it can't, the only possible 16-year sets actually do each have an equal number of R's and D's. There are 8 D's and 8 R's in every single one of these distributions. In fact, this covers all 16 possible distributions, presuming that you have to keep 8 in a row. Anyway, the point is we have all 16 possible distributions here, and I'm going to come back to this slide in a second. This is doing some work for us that's going to help us understand hopefully what's going on. But then I built this thing, and if you saw me cycle through these yesterday, you know it did not initially look this nice, so I've done a little coloring. But anyway, I've got the same thing up here that you saw a moment ago, and then I have a randomly selected 16-year period. So this thing right here, you can see random between 1 and 16. It randomly selects one of these 16 years to start at, and then I have a little Excel magic that just lines up what happened starting in that year. And then here I have 10,000 guesses. So if you go all the way down, you can see, oh my goodness, 10,007. Yes, I set up 10,000 different guesses. So this is the simulation part. I've got basically like 10,000 people who are randomly guessing a starting year. And what I'm going to do is I'm going to compare that random guess to the actual year. And over here we have the evaluation of how we did. Everywhere you can see these lining up. So you can see the first 5 here are D in both cases, even though the years themselves are different. It will say 1. And then every time we're wrong, it will say 0. And so you can see if the actual 16-year period selected was the one that started in 1996, but the one we think that we're picking is the one that started in 1995, we would get 12 of these years correct and 4 wrong. Over here, I expressed that as a percent, and again, you can see I do that 10,000 times. A couple interesting things popped out when I got to this stage of the simulation. One, you can see it's always an even number of years that we get correct, presuming we are just selecting from actual distributions of the presidencies. The reason for this is relatively simple, though a little bit sneaky. Consider this first scenario that started in 1990, so that's 3 years of George H.W. Bush, finishing up over here with 5 years of George W. Bush. If we had the actual scenario starting in 1990, but for some reason we thought it started in 1991, well, obviously we would just shift everything once to the right. But what ends up happening there is that means we're going to have one miss at the end of George H.W. Bush's presidency, and that has to be paired with another miss at the end of Bill Clinton's presidency. So the misses always end up being paired. So it's actually not, we look at these 64 possible selections, we think of them as 64 coin flips, and we think, oh my gosh, there's so many possibilities. But when we do this in terms of these presidencies and these 16-year sets of times, you can tell we start to reduce what's possible really quickly. And so now looking at this, I can tell, oh, there are only a few possible outcomes as to how many years I could get correct. Finally, I averaged these all together, and I did 4 different calculations because I wanted to show you how in a probability simulation, or even if we were actually working this out somehow, like if we were slowly adding up the data from Dan Meyer's activity, in some small number of trials, you wouldn't necessarily expect it to be right on top of that 50% expected value, if indeed it turns out that that's correct. Again, the whole reason we're simulating this is maybe that's not going to be correct. But as we increase the number of trials, or in the context of the activity, as more and more people do it, you would expect it to regress toward that expected value, to kind of coalesce toward that 50% expectation, which is exactly what you can see here. After 50 trials, we go down to 55%. After 500 trials, we're actually slightly under 50%, but obviously awfully close, 49.65%. It is a little interesting to me that over the next 9,500 trials, we only change by 0.07%, and it does actually change downward, so it kind of moves away from the 50% expectation. It could be that maybe this is because our expectation actually is too high. Something is happening in terms of the distribution of presidents, like I expected yesterday, that's causing the expected value to be lower. But as we run some more of these simulations, if I just get Excel to run some more, you can see, 50.03, 49.84, 50.10, 50.21. It's all pretty close to 50%. In fact, I have another document somewhere here, where I've actually gone through, this column you could ignore for now, I'll talk about that in a second, but I've actually gone through making the assumption that we know the distribution of presidents over some certain years, and we're guessing based on that knowledge. You can see it is really, really close to 50%. Because this was contrary to my expectation, I wanted to go ahead and make sure if we were just guessing at random, that maybe that wasn't higher or lower than what I expected yesterday. And so I built another little random guesser. This one does not guess from the distribution of actual presidencies. Instead, exactly as you can see here, this is answering the question, what if we do just randomly select an R or a D? And again, I've got a little evaluating function. Now that we have separated out the runs of presidencies, now that we are just guessing at random, you can see we've got some odd numbers in here. We can get an odd number right. And yet still, as we look over the 10,000 trials, we see a number really, really close to 50%. You can see we've got some differences, again, upwards of 60% after just 10 trials guessing at random, but then very quickly within 50 trials, we are quite close to 50%. And it doesn't matter how many times we run these 10,000, you can see the numbers stay in that vicinity. Obviously, oh my gosh, 50% right on after 10 trials. That's funny. But you can see the numbers just don't deviate that much. In fact, in this document over here, that is what this column was for. What percent answered correctly when guessing completely at random? Again, each one of these represents 10,000 trials. I keep thinking of 10,000 spoons, 10,000 spoons. I keep thinking of 10,000 spoons. But anyway, you can see after 260,000 guesses, we are just a nudge under 50%. And so I just don't see a statistical reason to think our expected value is going to be different based on a simulation than what we figured out yesterday based on probability theory. I do think I figured out why, though. I figured out why I had a misimpression about this. I was thinking that based on the 31-year span, and based on the fact that there were more Democratic president years than Republican president years in that 31-year span, that it was going to shift the numbers one way or another. But again, you can see what actually ends up happening is, presuming we are right on, we get 16 right. And again, as we shift our error once to the right or once to the left, we always lose 2. So we go down to 14 right if we're 1 year off, 12 right if we're 2 years off, 10 right if we're 3 years off, 4 years off, 5 years off, 6 years off, 7 years off, and after 8 years off, we are perfectly uncorrelated with the actual answer, right? That's when we get 0 correct. But then after that, even though we're now 10 years off, when we're 9 years off, now we actually start to kind of get lucky and we pick up 2 more. 10 years off, 11, 12, 13, 14, where if we're 15 years off, we're almost all the way back to the beginning and we get 14 of those years right. In fact, you can even see some numbers I've put together down here. We can do our same expected value calculation that we did yesterday. So that 16, where we get all 16 right, that happens 1/16th of the time. And so if we're doing our expected value calculation like we were yesterday, we would now do 1/16th times 16. And then this 14. Well, as I showed you, this actually ends up showing up twice because we can either be really, really close to the right answer or actually really far away from the right answer. But either way, it ends up giving us 14 correct responses. So 2 out of the 16 times, we get credit for 14 correct responses. We can do the same thing from there. 2 out of the 16 times, we get 12 correct responses. 2 out of the 16 times, we get 10 correct responses. 2 out of the 16 times, we get 8. 2 out of 16, we get 6. 2 out of 16, we get 4. 2 out of 16, we get 2. And then finally, of course, the flip side to this 1 out of 16 scenario where we got them all correct is a 1 out of 16 scenario where we get 0 correct. As you might imagine, when we add all this up, what do we get? You guessed it, we get on average 8 correct responses out of 16. You can see in Excel, I've added all of those together. Right down here, Excel tells us the sum, 8 out of a count of 16 possibilities. 1 in 2, 50%. So, my apologies to Dan Meyer. I should have trusted you. 50% is the expected value. We can see it theoretically. We can see it by simulation. There's no getting around it. People are answering correctly less often than you would expect, even if they were just guessing at random. They're not guessing at random. I don't know if that makes you feel like they're doing better or worse, but something interesting is going on there to be sure. Oh, there was this one thing. Do I want to say anything about this? You may have also noticed that it would be nice if we could recognize some kind of pattern based on the numerators of these fractions when we were doing some of the theoretical probability yesterday. 1, 3, 3, 1, 1, 4, 6, 4, 1. I guess this will be my additional challenge for those of you who don't already know where I'm going with this. You can put these numbers in a special arrangement together called Pascal's Triangle. I bet if you're not familiar with this, you can look at it and figure out the pattern. So try to figure out the pattern if you don't know it already. But we can use these numbers for our theoretical probabilities. They're related to something called the binomial coefficient, which I'm not going to give away otherwise. And in any case, what this was right here was my way of calculating, well, those 31 correct responses that we're getting on average out of the 64 slides, we would expect to get exactly 31 just under 10% of the time. Just like I showed you yesterday in this kind of Wolfram Alpha calculation, 32, the most popular response, we would get, again, just under 10% of the time. Well, I just thought to myself, it's worth remembering that these outcomes that are pretty close to getting them half right, if you add the different probabilities together, you can see almost half of the responses should be, if we were doing this at random, somewhere between 30 to 34 out of the 64 slides correct. And so in that sense, although 48% is less than random chance, it's not like wildly far away from random chance. Although again, as you saw when I did the trials, after about 500 people or 500 trials, we would expect it to be pretty close to 50%. So again, that is still something interesting happening. But anyway, I'll have to say more about that in another video. I know why you're here. I know what you want. You want the giveaway, right? I did not prepare a fancy spreadsheet for this, although I should have. Didn't color it or anything. These are the different comments. I tracked them by URL. I don't know who this is. You're about to find out right now. Let's assign a random number because I've already said a bunch about Excel. I'm just going to keep this simple. Let's copy that and go all the way down. 46 commenters. Thank you so much for your comments on the videos. I can't count likes and subscribes. I know that's like against YouTube law, but or maybe you can't. I can't figure out how to find out like who liked on a video or who subscribes to the channel. So I had to do it by comment. If you only liked and subscribed and didn't comment, I am sorry to say you're not in the running for the iPhone 8 box. But in any case, if you did comment, if you're one of these 46 comments, you could win right now. What I'm going to do is I'm going to say, hey, Excel, sort yourself. Sort by column I. Smallest to largest? No, let's go largest to smallest. Click OK. I can hear my baby crying in the other room. I'm so excited. There's a URL. Copy. All right, here we go. Who's going to win? Who's going to win? Who's going to win? Highlighted comment is Ace Wilburn. Hello, you are the highlighted comment. You win the iPhone 8 box. Congratulations to you. If you are Ace Wilburn, you win the box. If you're another commenter, maybe I'll do another giveaway. I don't know. If you're just a random person coming across this, thank you for watching all the way to the end, particularly being that there's a contest you can't possibly have won, but maybe I'll do a contest in the future. Do you want some other random boxes? I've got a mask here. Do you need a mask?